Okay, so thank you very much for this occasion to talk about a work that I've been interested in for quite a long time. I will try to present a very broad overview of this work, and of course I will explain all these terms in the course of the lectures. But the first one will be really focused on a very key ingredient in all this business, which is the Boltzmann equation. So maybe some of you will be a bit disappointed because they know everything about the Boltzmann equation. So I apologize to those of you who are really specialists about this. Then the second course will be about, so this is a limit, and so this is, we will see that there is a kind of probabilistic setting, and so in this setting, actually this limit has to be, so the Boltzmann equation will be essentially the law of large numbers in this limit. Okay, so I will show that the Boltzmann equation can be seen as the law of large number associated to this dynamics in this specific limit. So of course I will explain everything here, and this will be really the content of the second course. Then the third course will be about, say, so this derivation, the first rigorous derivation of the Boltzmann equation starting from this R-sphere dynamics actually goes back to Lanford, who was a professor here. But then there are some alternative proofs, and I will try to present one of these alternative proof in the third lecture, because somehow it allows to present a very important ingredients as well, which are the dynamical clusters. And the reason why these dynamical clusters are important is that, so first of all, they seem to be a key ingredient in the recent proof by Deng, Annie, and Ma. So this proof, so the theorem that they seem to prove is that actually they have a global convergence, so really improving the result by Lanford. And these dynamical clusters are also a key ingredient to look at the fluctuations. So of course in probability you can just look at the law of large number, and then you can also look at the fluctuation. So that's what I will do in the last course. So just fluctuations. So by fluctuation, I mean kind of central limit theorem and also large deviations. Okay, so that's the plan of the course. And in each lecture, I will try to have a first hour which is really non-technical to present all the ideas, and then maybe a second hour where I will go a little bit more in the technique. But still, I will try to remain at a level where everybody can understand, and of course feel free to ask questions. I think it's important in the course that everything is clear. And
so the big problem of Lanford proof was that the time scale was extremely short. They were
exactly. So this is the
announce whether now there is a theorem where there are many collisions and the Stoss-Zal ansatz is proven in some sense.
So that's what is announced in this paper by Deng, Annie, and Ma. But okay, we have already spent, I don't know, maybe something like 300 hours trying to read the paper, and at this time I'm not able to check that everything is correct. But this, okay.
That's what they claim, that it's a long term.
Exactly.
Okay.
Yep. Okay, so let's start with this important equation, so the Boltzmann equation. So the first thing that I will do is just to explain that this is the master equation of kinetic theory. So what it means to be a kinetic model? A kinetic model means that you try to have a description of a gas, say, which is a statistical description. Okay, so here the unknown is just a distribution of probability, f, which is a function of, say, time, position, and velocity. So that's the position of the particle. V is the velocity. And so f is the probability of finding a position with a particle with position x and velocity v at time t. Okay, so that's really, and I think it's really something which is interesting in the work by Boltzmann. I think it's the first time that someone wrote an equation for an evolution equation for probability. Okay, so I think from the historical point of view, it's really interesting to see that it was really a different way of describing the evolution of a gas.
Is it a probability or a number? Usually in physics,
so
it's a number of particles in some of it. Yes.
It's a density of particles. So either you renormalize everything to get a probability, okay, and so this is just a matter of normalization. If you divide by the total number of particles, this will be a probability.
It's different probability than just number. Okay.
So that's just a matter of renormalization. Here I will just assume that it's probability, so the integral with respect to x and v is equal to 1. Okay?
There is all the work by Bogalubo. How is on derivation of kinetic relation? How it is related to this?
I will talk about this in this second course. So at the moment I will just first write the Boltzmann equation. Okay, so the Boltzmann equation consists of two parts. So the first part just describes the transport. Okay, so it means that if you have a particle of position x and velocity v, and it has no collision, nothing, and no external force, nothing, then you will just, so what you expect is that at time t, it will be at position x plus tv. Okay, so this part is the transport. Okay, so if you have transport without external force and without interactions, then the equation for f is just dtf plus v grad xf is equal to 0. Okay, you can check that with this equation, the solution of this equation is just that f of txv is just f naught at position x minus vt and v. Okay, which means exactly that you will just say transport the density along this characteristic line x plus vt, and the velocity is constant. Okay, so that's just the transport part. And now in the Boltzmann equation, what you would like to describe is the effect of collisions. Okay. And this is the point where the model is statistical. Okay, because of course you will not be able to track all collisions of all particles in a deterministic way. And so what you will do here is to say, okay, I will just keep the information that a particle at a point x will change its velocity, so kind of its jump process, will change its velocity with a certain rate, which is, so it's really a statistical process. Okay, so I will write this collision operator and then I will explain. Okay, so here, if you take into account collisions, you will still have the transport part. Of course, all the particles will just move with their own velocity. And now it will say the time derivative here. So this is really a time derivative along the characteristics. It's equal to some collision operator. So the first remark is that this collision operator is quadratic in F, meaning that you only consider binary collisions. Okay, so The second thing is that this will be an operator, so an integral differential operator, acting only on the variable v, meaning that you assume that the collisions are completely pointwise both in t and x. Okay, so they are pointwise in t and x. So this binary collisions correspond to the fact that it's quadratic in f. The fact that it's pointwise in t and x tells you that the q of ff is just acting on a v variable. Okay, and then you will also assume that these collisions, they are elastic. So that, say, if you have a collision between two particles with velocity v and v1, then you need that after the collision, the velocity, say the total momentum is conserved and the energy is also conserved. Okay, so you will look at all the velocity such that v plus v1 is equal to v prime plus v prime 1, and v square plus v1 square is equal to v prime square plus v prime 1 square. Okay, so this means that if you have a sphere like this, so if you have your velocity v here, you will hit another particle with velocity v1, and then after the collision, you will have two particles of velocity v prime and v prime 1, but this v prime 1 is another diameter of the same sphere. Okay, to ensure that you have all these conservations, so conservation of momentum and conservation of energy. Okay, and actually you can prove that you can parameterize all the v prime and v prime 1 satisfying this relation by just an angle here on this sphere. Okay, so now let me write this q of ff. So it's a bit. So now it's a function of v, t, and x. They are just okay. Here they are just parameters. Of course, this is function of t, x, and v, but I will not write t and x just because they are the same everywhere. Okay, and now you have an integral here of f of v prime 1 minus f of v v1, and you multiply this by b of v minus v1 omega, and then you integrate with respect to v1 and omega. Okay, now I will explain. Okay. So here, this first part is what is called the gain part. And the idea is that maybe you will have new particles of velocity v, not because you have new particles, but just because you have two particles of velocity v prime and v prime 1. At some point, they collide together, and then they change their velocity, and then you have a new particles of velocity v. Okay, so this corresponds to a creation. It's not a creation, but just the fact that as the result of this collision process, you have a new particle of velocity v. Okay. Now this is the loss part, and this corresponds to the fact that maybe at some point a particle of velocity v will hit another particle of velocity v1, and they will change their velocity, so going to something different, and then you have less particles of velocity v. Okay, so here you see you have a plus sign for this, because this corresponds to new particles of velocity v, and a minus sign for this, because you have less particles of velocity v. And now what you have to prescribe is somehow the law for this jump process, and this law for this jump process is given here by this cross section. And this really tells you the probability of going to this pair v prime 1 to the pair v1. Okay, so this is really the rate of the jump process. Go from vv1 to v prime 1, or v prime 1 to vv1. Of course, with the constraint that v prime 1, they cannot be everywhere. Okay, so now you see that with this, you have v prime, which is v minus v1 dot omega. That's the parameterization here by this omega, and v prime 1 is equal to v1 plus v minus v1 dot omega omega. Okay, so this is really a parameterization of all velocities that satisfy these conservations. Okay. Okay, and now for all possibilities, you have a jump rate which is given by this. Okay. Okay, of course this is a function which is non-negative. This function actually tells you something about the microscopic interaction, so I will come back on this when I will look at the Boltzmann equation as the limit of something, okay? But somehow it really tells you that's the only information that is kept on this microscopic interaction, okay? So it really depends on the microscopic interactions.
So you are considering only two-body collisions, only two particles collide?
Yeah.
Yeah.
A naive question. Okay, the interaction is elastic, but if you go to very close to the infinite time or go at time, okay, so maybe there are too many interactions and you are getting maybe slightly out of this range of...
Yeah, so that's really what is important here in this low density limit, means that somehow all the multiple collisions will be negligible compared to the binary collisions. Of course, this is something that you have to justify if you would like to show that the Boltzmann equation is a good approximation of the dynamics. So that's part of the problem, actually. But right now, I just say, I consider this equation with, and that's it. Okay? So maybe I should comment a bit on this cross-section now. So I think that's the... So I told you that somehow it keeps track of the microscopic interactions. And so we will see that for mathematical purpose, we will need some assumptions on this cross-section, which are the cutoff assumption by grad. So we will assume that we have bounds from below and also upper bound on B. Okay, so I will just write this. So I will assume that the B of V, say of Z, and omega is smaller than a constant time 1 plus Z to the power beta for some beta which is between 0 and 1. Okay, and I will also assume that B of Z omega, if I integrate respect to omega, is bigger than a constant times Z over 1 plus Z, something like this. I will just check that it's what I need. Yeah. Of course, this is not the same constant. Okay. That's C1 and C2, C plus and C minus. Okay, so I will explain why these assumptions are important and why it's not true in all situations. So in the art sphere case that I will study this assumption, they are true. Actually, the B is essentially Z. Okay, that's just essentially it's V minus V1 dot omega. Okay, so in the art sphere case, essentially you have that B of V minus V1 and omega is just absolute value of V minus V1 dot omega. Okay, but, and then you can compute this and it's, of course, it's not a problem. Okay, but say, as soon as you have long-range interactions, whatever the decay at infinity, you see that this first assumption here will not be satisfied. Okay, because this is the problem of what is called grazing collision. Okay, actually you have a lot of collisions which will, okay, modify very little the velocity of the particles, but still as a result, this is not integrable. Okay, so yeah, there is really a problem of integrability of the cross-section. So even a weaker version of this is not true when you have this grazing collisions. Okay, so, but say in the R-sphere K that we will be interested in, it's not a problem. Okay. Okay, so that's the first thing that I wanted to say is what this Boltzmann equation, how it can be stated. Okay. Now I would like to comment a little bit more about the physics behind this this equation, and I will give you the main physical laws, which are, say, macroscopic, maybe laws which are associated to this equation. Okay, so the first thing that I wanted to say is that there is a very important assumption in this equation, and maybe I didn't make it very clear, is that you have exchangeability. Okay, so the first really important thing is exchangeability. What it means that the particle v and v1, so 0 and 1 with this notation, they play exactly the same role. Okay, they have the same mass. There will be you can just exchange the particles and you get the same thing. And you say it's really important. If you have a statistical description, of course, you need somehow that all the particles are the same. If not, it's a bit strange. Okay, so this exchangeability means that essentially you can exchange v and v1, and the Jacobian of say the integration, it will not change. So the Jacobian of this will be 1, and everything will be essentially preserved by this change of variable. Okay, so that's the first thing. And of course, you see that exchangeability will be really also important when we look at a law of large number. You need that somehow all the variables are symmetric. Okay, the second thing is this microscopic reversibility. So maybe I should say here that the B will depend only on the modulus of v minus v1 and not on also you can change the omega, but essentially you can change v and v1. Okay. Now the microscopic reversibility tells you that you have the same probability to go from v prime v'1 to vv1 than to go the other way. Okay. So the jump process has this symmetry that it's the same to go from a state to another state and to go back. Okay. So when you look at this, actually this is an involution. Or maybe it should change the sign of omega, but okay, that's maybe the involution is the one with the minus omega here. And you have the same jump process. Okay, so the B is invariant under this change of variable, changing v and v1 and omega in v prime v'1 and omega. Okay, so these are really these two properties that can be seen somehow in the B here. Okay, so the B is invariant under this change of variable.
Isn't there also an assumption that there is no extra integrals of motion? That only you account for standard integrals of motion like energy and momentum, but there are some systems with higher integrals.
Yeah, there are actually you can.
There are even completely integrable systems for which the motion would not work, right?
I'm not sure I understand completely your question, but what I say is that this Boltzmann equation is the simplest one you can imagine. Of course, you can imagine systems which are more complicated than just particles determined by just their position and velocity, and then you get more complex version of the Boltzmann equation. So The fact that I choose that each particle has 2d degrees of freedom, so d for the position and d for the velocity, is somehow the simplest possible assumption, but it's not really restrictive. You can imagine doing something more complex. Okay, so now with these two properties, and you see that it's really, I think it's really fundamental to understand that at this level, you assume that somehow the microscopic dynamics behind all this, you have exchangeability and reversibility. Okay, and now starting from this, you can derive a lot of important properties, and so I will do this computation because I think it's really important to see this at least once. So now if I take this Q of FF, so once again I will not write all the T and X, they should be everywhere. Here you have T and X, here the same T and X, T and X, T and X, T and X everywhere. Okay, so now I would like to integrate this Q of FF against a function phi, which is just a function of v, okay, which is a test function, okay, just to see how this symmetry assumption, what they will tell me, okay. So of course I can write this, and you see that, so this will be the integral with respect to v, v1 and omega, and I have this b, okay, maybe I should write this, so the b dv dv1 d omega. And now what I have to integrate is this f of v prime 1 minus f of v1 times phi of v. But now you see, if you use the first assumption here that you have exchangeability, you see that v and v1, they play exactly the same role. Okay, and now I integrate with respect to v, v1 and omega. And b is symmetric under this change of variable, exchanging just v and v1. Okay, so this means that I can replace here the v by v1, or just change this as the half sum of phi of v plus phi of v1. Okay, so this is equal to 1/2 of the same b dv dv1 d omega, and now you have f of v prime 1 minus f of v1, and you have here the half sum phi of v plus phi of v1 divided by 2. Okay, the 2 was already here, just once. Okay, so that's the first remark. Now the second remark is that I also know that I can exchange the pair VV1 and the pair V'1 for the same symmetry reasons, because of this microscopic reversibility here. Okay? And so now let's do that. You see that there is something which will be changed, is the sign of this guy. If I exchange VV1 in V'1, this will not be changed, but the sign of this guy will be changed. Okay? So what I get is that it will be 1/4 of B dV dV1 d omega. Then I have this guy here, f of V'1 minus f of V1. And then I have the phi of V plus phi of V1 minus phi of prime minus phi of V'1. Okay, so I have this minus sign just come from the fact that if I exchange V and VV1 and V prime and V'1, I will change the sign of this. Okay, and this is true. Of course, I didn't say anything about the regularity assumption, the decay at infinity, and blah blah blah. So for at the moment, it's just a formal computation. But you see that it should be true for any test function, reasonable test function phi, and for any function f. Okay, so this seems to be just a simple computation, maybe not very interesting, but you will see that just from this, you can deduce all these important physical laws. So the first physical laws are the conservation laws. So now you see that I assume that V plus V1 is equal to V prime plus V'1. I know this. This is just by definition. And also the conservation of energy V square plus V square v1 squared is equal to v prime squared plus v prime 1 squared. And also there is another thing which is also true. Maybe it's not that 1 plus 1 is equal to 1 plus 1. Okay, so 1 plus 1, these are just the two particles, so the mass at before the collision and the mass after the collision. It just preserve the number of particles. Okay, so if you use this and you take phi here to be either 1 or v squared, you see that this part here will be exactly identically equal to 0. Okay, so this tells you that you have that the integral of q of ff against 1, which is 0, that the integral of q of ff against any component of v will be 0, and that the integral of q of ff against v squared is equal to 0. Okay, that's just a result as a result of these two properties of exchangeability and microscopic reversibility. Okay, of course you see that if you assume that each elementary collision preserves the mass, the momentum, and the energy, say in average, the same quantities are preserved. This is not very surprising. Okay, this is just that everything which is true for each collision will be true in average. Okay, and so you see that now you can take the equation which is here, and you can integrate against 1v and v squared, and this will tell you that you have conservations. Okay, so this implies that dt of the integral of f dv plus the divergence of the integral of fv dv is equal to 0, and that's the conservation of mass. Okay, so that's the number of particles or the probability, so it depends on the normalization, but and so this is here just the current. Okay, so you get that's the flux, the momentum flux. Okay, so this is just maybe the equation that you sometimes write dt rho plus divergence of rho u is equal to 0, which is the usual conservation of mass for fluids. Okay. Now you can write also the conservation which is associated to this momentum, and so you get that the integral of fv dv plus the divergence of fv is equal to 0, and so this is the time derivative of rho u, which is equal to something, and here you see that it's not really an hydrodynamic model because it's not clear how you can compute this momentum flux, say with usual thermodynamic variables. Okay, so here there is something which is missing to get really hydrodynamic equations. They are still at the hydrodynamic level, at the fluid levels, but and then you get the same for the conservation of energy. Okay, maybe the energy you should write this with 1/2, but okay. Okay, so these are fluid equations. Of course, this is not a closed system of equation. Okay, it is not the Boltzmann equations somehow contain more information than a fluid model because somehow you will not prescribe that, say, this f has a specific profile in v, and then that you can somehow replace this just by a simple function of thermodynamic variables as temperature, pressure, and so on. Okay, so but still, these 5 or d+2 equations, they are fluid equations. Okay. Okay, so but at this level, there is no surprise. You assume a lot of symmetries and a lot of conservation at the microscopic level, and then you deduce that at the statistical level you have the same. Okay. Now there is something which is a bit more surprising, which is what is called the H theorem, which is the reason why this Boltzmann equation was, say, really a breakthrough. So I said that it was a breakthrough, first of all, because it was the first time that someone wrote an evolution equation for a probability, but it's also a breakthrough from really the physical point of view, because it's the first time, so this H theorem will be just a mathematical formulation of the second principle of thermodynamics. Okay, so that's the same as second principle. Maybe it's even more precise because we will see that you have an explicit formulation for the entropy dissipation. Okay, so now I just go back to this the same identity here, and now I choose for phi the function log of f. Okay, I can choose phi to be log of f. I say I can choose it, but of course it depends on all this integrability, blah, 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 at infinity. Okay, and so now if I take here log of f, what I get here is log of f of v plus log of f of v1, but as the logarithm is additive, this is just the logarithm of f of v1. Okay, so I get that this is 1/4 of b dv du1 d omega. And now I have f of v prime 1 minus f of v1. And I multiply this by log of f of v1 minus log of f of v prime 1 f of v prime. Okay, so here I just use the additivity of the logarithm, but now I can also use the fact that the logarithm is an increasing function, and you see that this guy has a sign. Okay, so I will write this as minus d of f, so minus the dissipation, because and d of f will be non-negative. Okay, and you see that's just a very simple computation. Okay, and this is. And so I can do exactly the same as here, and can just multiply this equation here by log of f minus 1. So this will be just the derivative of f log f. Okay, and what I get here is that this implies that dt of the integral of f log f plus the divergence of f log f v dv. This is equal to minus d of f, and so it's negative. Okay, so here I will probably at some point disagree with physicists because, say, in mathematics we call this entropy, and this is actually minus the entropy of physicists. So it's okay. So we call this.
And H was meant eta, no?
Yeah, it's the
Not H. By the way, the question of Sasha was in your list of conservation if you have another conserved quantity. If you have another phi of v where you have 0, does it change what we are going to hit? That was.
Not really. So for instance, if you take some, say, instead of sphere, you can imagine that you have ellipsoids at some points, and then you see that in addition to this momentum and energy, then you have also an angular momentum, and then you can so you have more variables somehow, and then you have more conservation, and it's not really a problem.
But with less variables and more conservation.
Ah, less variable?
No, the same number of variables, but more conservation.
This I don't know.
Where you explore only a subpart of phase space. That was the question. Whether you can still prove something, or you are somewhere assuming that you are not, that you are ergodic in that sense, that you have only these conservation laws. That was the question of Sasha.
It should be assumed, otherwise there is false on
I think probably the proof at some point will fail. If you have So I cannot say this. I'm not completely sure, but we will see that it's complicated because in the proof, actually, we are not able to really use the fact that you have kind of ergodicity. But still, we are using the fact that, say, in a very, say, without understanding anything, because actually the problem of the proof is that we don't really understand what happens. So that's, say, from the physical, you will see that from the physical point of view, it's really disappointing because we can prove a theorem, but from the physical point of view, this theorem is not relevant at all. Okay, so we don't really understand what happens, this question of mixing and so on. So I would be tempted to tell you that if you don't have this mixing, probably it's not true that you can have a description like the Boltzmann equation. But at the same time, with the kind of proof that we have, it's not clear what we say, how much they can be extended or not. But maybe I will comment more on this later on when we will.
Another trivial question. Here you have Galilean invariance. If you are relativistic, okay?
Yes.
Does it change something, or it's just a trivial extension instead of v squared or relativistic?
No, you can write a relativistic Boltzmann equation just changing v divided by.
But the proofs, all the proofs goes.
So the proof, I think, say, to my knowledge, they are not written, but I would expect, say, I don't see what would be really different. I don't think it would be really different, say, at least for, say, in the case, in the relativistic, so I don't know what to say in English, but relativité restreinte. Yeah, I think it would be essentially the same. And of course, say, general relativity would be different because, say, the starting point would be so different that I don't know.
Could it be that your assumptions about the cross-section rule out actually additional conservation laws? Because conservation laws, if we impose extra conservation laws, we know that only very special kind of cross-sections are going to be allowed.
So this will be mostly to get a nice theory of the Boltzmann equation, and we need this nice theory of the Boltzmann equation. Actually, that would be my second part today, to tell you what we know from the mathematical point of view on this Boltzmann equation, and we will see that somehow the setting where we are able to derive this Boltzmann equation from the microscopic level is already a very, very restricted setting compared to what we are able to. And so this assumption is essentially, say, from the formal point of view, I don't think it's really required. But you will see at some point where it's important. Okay, so for instance, if we don't have this assumption here, we can introduce weaker solution of the Boltzmann equation and still have a Cauchy theory. Okay.
Suppose you're in 2 dimensions, and the only type of scattering which is allowed is when velocities are exactly reversed.
Yes.
That would correspond to an integrable situation.
Yes.
Of the kind that Sasha and Tibor mentioned. Does this satisfy these assumptions on scattering?
No, and we know that in this kind of situation. In this kind of situation, so for instance, if you replace spheres by squares in 2 dimensions, then it's proof that you don't get the Boltzmann equation, but something different. Okay, so if you start from a situation where instead of having small balls like this, you have small square, and you see that the reflection law for these squares, they are somehow maybe more trivial, and say you have only 4 possible directions. Okay, and then you see that somehow some averaging is missing, and what you get is not completely clear what you get, but it's clear that you don't get the Boltzmann equation. Because somehow behind the Boltzmann equation you really have, but this will be probably easier to discuss afterwards, but you have said the probability of having recollisions, and so to have a lot of correlation in such a gas is much more important than in the R sphere gas. Okay, so somehow if you add some rigidity in the system, in the microscopic system, then you expect correlations to be more important, and then the Boltzmann equation should not be a reasonable model. So maybe it answers a little bit the question in the case of, say, integrable models. You expect to have a lot of rigidity, and so maybe there is not enough averaging. But I cannot really answer because I have no theorem telling this exactly. But at least for these squares, this is clear that it's not the Boltzmann equation. Okay, so the last part of this, say, introduction, say, more formal things is about irreversibility, because I think it's really something which is important. Okay, so I think that's the third thing. Okay, so because you have this inequality here, you see that dynamics, which is described by this Boltzmann equation, is not reversible. Okay, so if you have this so kind of experiment that you can just thinking experiment. Okay, you see that if you start from initial data, you let the system evolve, okay, and at some point you decide what would be something natural for a billiard to change all velocities in their opposite. Then in a billiard you would expect that all the particles will come back to their original state. Okay. Now if you do the same here for the Boltzmann equation, you see that it cannot happen. You start from some f naught, okay, you let the system evolve, then you see that this entropy or this opposite entropy, so this integral f log f will just decrease, okay? Then you can exchange all the velocities in their opposites. It will not change this h function. And then you can still evolve the system with the same Boltzmann equation, and the entropy will still decrease, and then you cannot be back to the original state. Okay, so the fact that you have a Lyapunov functional tells you that the evolution is irreversible. Okay, so you have a Lyapunov functional, which is the integral, say, of f log f, and then integrate with respect to v and x. And this quantity is just decreasing, so we cannot go back. Okay, so that's really something which is important and which has been really problematic at the time of Boltzmann, and what I would like to tell you at this stage, and I will of course comment more later, is that this quantity here, so this h function, actually it's a quantity which is very different from an energy or a mass or all these extensive quantities which correspond to things that you can measure from the physical point of view. Okay, this is more related to information. Okay, so this tells you something about information. And actually, all these things, they are also somehow the very first steps of information theory. Information theory is constructed, say, according to the same way of thinking, I think. Okay, so you see that irreversibility is not the irreversibility of the dynamics itself. You see that at the microscopic level, I assume reversibility, maybe just reversibility in a probabilistic setting, which is not the same as really a deterministic reversibility. But even though I have reversibility at the microscopic level, this doesn't tell you that you have reversibility at the statistical level, because the question is what kind of information you keep on the system. Okay, and so what I say is that the dynamics itself can be reversible, and that the information that you keep on the system maybe is not, and that's exactly what is the case here. Okay, so what is not reversible is not the dynamics, but what you keep as information on the system. Okay, so the fact that so this irreversibility. probability, just a loss of information. And I think it's really important to understand that it's really a statistical thing. So maybe you can just walk in the streets, say I have turned left and then right, okay, and then right. So of course, if I tell you this, you can go back, okay. If I tell you, oh, I turn 4 times, twice on the left and twice on the right, of course you will not be able to go back. Okay, so that's really the kind of information that you keep on the system, which does not allow to go back. Okay, so and this is due to the fact that you have a statistical description. And this is really important because this kind of paradox of reversibility, which was mentioned by Laure, was really a very strong argument against Boltzmann theory. Okay, so that's really say the way we should understand this Laure paradox. There is no paradox. Dynamics can be reversible, and information maybe not. Okay, and then maybe 2 other things that I would like to say about this irreversibility. So the first one is what happens for very large time. Okay, so for a very long time, what you expect, of course, is that say what you would like to have is that somehow this entropy dissipation, of course, if everything is integrable, you expect that at some point it will just converge to 0. Okay. And of course that this guy will somehow converge to its minimum. Okay, and then of course it's not clear that it's true. You have to prove something, but at least it is what you expect. So what is expected as t goes to infinity is that, say, d of f go to 0, and h of f converges to its minimum. Of course, with the constraint that you should preserve all the conserved quantities. Okay, so under mass, momentum, and energy constraints. Okay, so you can use both things to, and actually one is enough, to prove that if you just try to minimize this integral of f log f under the constraint that the integral of f of v, and f of v squared are conserved, then you get that the log of f should be a linear combination of, so you get that log of f. So using this, you obtain that log of f should be something like alpha plus beta dot v plus gamma v squared. Okay, so that's the minimization under constraints. And if you try to use the fact that the entropy dissipation should go to 0, you get that f of v prime 1 has to be equal to f of v1 for any v prime and v prime 1 which are compatible, and then you get the same. Okay, so this is the way you get this, and this you get that of for v f of v1 has to be equal of this almost every v1 and omega. And this will also tell you that, so you can take the logarithm of this, and once again you get that the log of f has to be a linear combination of 1v and v squared. And so this tells you that in the end you expect just f to be a Maxwellian. So you see that at the moment I didn't say anything about the dependence with respect to x. So this will be something like rho divided by 2 pi t exponential of minus v minus u squared divided by 2t. Okay, so that's the Maxwellian distribution. with density rho, temperature T, and bulk velocity U. Okay, and so of course here you see that I didn't say anything about the dependence with respect to x, but you see that essentially that there will be this conflict between the transport and the dissipation. So the dissipation tells you that locally for any x you should be something like this, but then the transport tells you that you have no choice, you should be uniform with respect to x. Okay, so what you expect actually is not that only that, so infinity, f infinity is of this, if like this for any x, but this is the same, so for, you can just add this, and rho u and t that will not depend on x.
You are not assuming that one is in a box somewhere?
Here I assume that I'm in a box, and if I'm in the rule space, I will just consider a situation where at infinity I'm a very small fluctuation around something which is already an equilibrium. And I will not discuss here, there will be a lot of things to say about boundary conditions and whether I am close to equilibrium and this kind of things. So here, for the sake of simplicity, I will just assume that x is torus without any boundary condition and v is an RD. Okay, just because I don't want to discuss these boundary conditions, this can be, of course, much more complicated. And actually, if the boundary conditions, so imagine, for instance, that you are just in a slice like this, and you have different boundary conditions on the left and on the right, then you are in a situation which is out of equilibrium, and then essentially we don't know much. Okay, so I will just consider this situation where... okay, so that's what I wanted to say for this first presentation of the equation. And now so for the second hour today, what I would like to tell you is what we know from the mathematical point of view on the same equation. Okay, so I will try to make it not too technical, but it will be maybe a bit more. Oh, maybe there are questions at this stage, or it's clear, or. Okay, so the first, so actually there will be 3 parts for the mathematical theory, because there are different ways you can try to approach this equation. So the first one is that I would like to say have solutions which are just satisfy the physical assumption that you have, say, finite mass, energy, and finite entropy. Okay, that would be a very nice setting. I would be very happy to say that if I just assume that at time 0 I have finite entropy, finite mass, and finite energy, then I can construct a solution of this equation. Okay, so that's so for those of you who are more familiar maybe with fluid mechanics, this would be really the counterpart of this Laure solution for the Navier-Stokes equation. Okay, so that's really counterpart of Laure solutions. Okay, the idea is really to say, okay, if just from a physical conservation and so on, what I know is that, okay, from this equation, you see that, of course, if I integrate with respect to x, all the fluxes here, they will just disappear because I have assumed that I have no boundary. Okay, so this tells you that the mass is conserved. Well, this quantity is conserved, but it's less simple to work with it because it has no sign. But this one is also conserved. Okay, so what I would like to assume is that, okay, what I know is that, say, at time 0, what I know is that this guy is, so if this is a probability, it's just 1. Okay, and that this guy is finite as well. And so it will be finite forever. Okay, and also I have this entropy inequality. So I would like to say, okay, maybe I have this H. So actually, H of F naught cannot be really finite because somehow there are some problems of integrability at infinity. You see that. Imagine that log of that F is just this Maxwellian, and you see that maybe the log of F will be. So what is usually assumed is that, so what you are looking at is I think in physics it would correspond to the free energy. So it's a combination of energy and entropy. It's also called the relative entropy. And I guess so it's related to this free energy. I'm not sure. Okay, so this guy will be just the integral of f0 log of f0 divided by m minus f0 plus m. So I will explain from a mathematical point of view, the interest of looking at this quantity here is that the integrand is always non-negative. Okay, so it's better to have a quantity which is non-negative to use it as a control or as an a priori bound. Okay, but now if you look at this, you see that this m is just the Gaussian 1 over 2 pi, say to the d over 2 exponential of minus v squared divided by 2. So this is just this absolute Gaussian. So now you see that the log of m is just a combination of 1 and v squared. So this will not really change this part here. And now this is just a mass, and this is just a constant. Okay. So there are the interest in looking at this quantity rather at the entropy actually is first of all that you have a non-negative quantity here. So that this is non-negative. And that's in the case where you look at the Wu space. So instead of looking at the torus here, you look at the Wu space. You see that there is no problem of divergence because the size of the domain is infinite. Okay, so this is still relevant when X is in Rd. Relative entropy can be finite. Just it means that somehow you force the system to be at equilibrium at infinity. Okay, so F naught will not be a probability. This will not be true in the Wu case. In the Wu space, this and this, this will not be finite, but this quantity can still be finite. Okay, so in the end, what I would like to do is to work only with this quantity, only with this, which is finite at time 0. Okay, that's that, and this is really the equivalent of in this Navier-Stokes case. You look at just a case where this is finite at time 0. You have finite energy. Okay, now what is the counterpart here is that you have only this finite relative entropy at time 0. Okay, so once again, in the case where you have in the torus, this is not very different from. Okay, that's what I would like to do. Say, okay, I start from this system. I have finite entropy, finite mass, finite energy, and then I can produce a solution. Okay, that would be good at least to know a solution of this system. Okay, so now what is the problem? The problem is that, so you see that this essentially at infinity, when f becomes large, it grows like, say, L log L. Okay? And now you see that if you write the equation, if you remember the equation, you have that Q of FF is a quadratic quantity with respect to F. So, of course, with respect to the velocity variable, it's just like a convolution. Okay, maybe I should write, so maybe it's still written here. Yeah. So here you see that, of course, you can say, oh, but this f of v and f of v1, and here f of v prime and f of v prime 1, so it's more like a convolution in v. Okay? And then it's okay. You can take two functions in L1 and then take the convolution of these two functions, it's fine. But now, if you remember that I just forgot to write the t and x just because they were the same everywhere, so what you have is t and x here, and t and x here, and the same t and x here, you see that now, as a function of t and x, this is just a product. Okay? And now if you have a function which is just in L1 or even in L log L, the product of two functions like this is not defined. Okay, so this means that under the only assumption that somehow the entropy is finite, it's not clear whether this Q of FF is well defined. Okay, so this means that if you would like to look at this equation, now you have to do something in order that maybe the Q of FF is not defined, but you can have an equivalent formulation of the equation where everything is still defined. Okay, so that's really the idea between renormalization, and I think renormalization here is very different from physics, but maybe there are some connections, and I would be very interested to understand whether there are really connections here. So the idea of renormalization is to say, okay, maybe I cannot write the equation for f, but I will write the equation for beta of f. Okay, and this beta I will not choose. I will just do it for you with the square root. Okay, so here I will look at the square root renormalization, because I know that here there are some people who are interested in Schrödinger equation. So Schrödinger, you see that you write the equation for psi, which is the wave function, and you never write the equation for psi square, which would be the equivalent of f. Okay, and you don't care that you cannot write the equation for psi square. So you should not care that here I write the equation for square root of f and not for f. Okay, so that's exactly the same as for Schrödinger. Okay, so now I write. So of course there will be some trouble with the square root of f because square root is a bit singular at 0. But say here in this first approximation, I will just forget about the So I will write this. Okay, and then I have 1 over 2 square root of f q of ff. Okay, that's okay. So now what I will try to show you is that with the square root renormalization, actually I'm very happy because I can define everything. Okay, if I'm not wrong, I will try. So the first thing is that, so I have 1 over square root of 2f, and now I will rewrite the q of ff in a slightly different way. So I have the b dv1 d omega. And now I will write the short notation f prime for f of v prime, f prime 1 for f of So what I have here is f prime 1 minus f1. Okay. But now this I can write as square root of ff prime and then square root of f1 to the square plus 2 square root of f. Okay, probably I will be wrong, but you will help me. Times square root of f. Is it okay? I think so. Yeah. Okay, that's just an identity. Okay. So maybe the 2 here is wrong, but I think it's okay. And now we can say, okay, now she's happy, but she seems a little bit strange. Okay, now I will try to show you why I am happy with this formulation. So the first thing is that now you see that of course, if f is in L1, square root of f more or less is in L2. Okay, so that's the first thing why I am happy. So is that that this function h, so the relative entropy here, will control more or less the L2 norm of square root of f minus, so essentially it's bigger than m times square root of f divided by m minus 1 to the square. And I think there is probably a factor 2 somewhere, but okay. I think it's okay. I have some note here. Okay, so there is 1/2, I think. Okay, so what I would like to define is that this, okay, up, and then I have 1/2. Okay, so you see that when f is very close to m, 2 square roots of f divided by m minus 1 is not very different from f divided by m minus 1. Okay, this has the same, say this. So this is really the fluctuation. So this is a kind of square root renormalization. Of f, and it's very good close to m. Okay, so if I'm not very far from its equilibrium, in a sense, then it's okay. And now this g hat, which is 2 square root of f divided by m minus 1, now this guy is in L2. Okay, with the m dv dx. Okay, but now I can also use the same kind of functional inequality. So here the functional equality that I use is that square root of z minus 1 square is smaller than z plus log the z minus z plus 1 with a 2 somewhere. Okay, with a 2, maybe not 2, I don't know. Okay, something like this. Okay. Maybe there is a constant. But now I can do the same with the entropy dissipation. Okay, because of course the entropy dissipation can also help me here. Okay, so now the functional inequality, so here I will copy because it will be simpler, that I would like to use. So that's the first control that I have, but now I can also use this at x minus y log of x divided by y. This is bigger than 4 square root of x minus square root of y square. Okay, so that's the same kind of functional inequality here. But then this tells you that the d of f control the integral. So they control the integral of some q hat m. And then there is a nu here that I will dx dv. So maybe there is just dv. And the q here is renormalization, which really is like this. Okay? So now you see that maybe I can just write this. Okay, I'll just write this. Square b dv dv1 d omega. There is a 4. No, maybe there is even no 4 because I don't know. Okay, maybe okay. There is a constant. Okay, so now what you see is that this guy is in L2 as well. Okay, so now I'm very happy because this guy is in L2 square. It's integrable. Okay, of course you have to be a bit careful with the b and but okay. Now this guy is in L2. The square root of f will just disappear with the square root of f here, and the square root of f1 is in L2. Okay? So it's just like magic. Everything is well defined. Okay, so I'm cheating a bit because, of course, the square root of f here can be singular close to 0, and so if this guy is bounded but you divide by 0, of course, it's not very good. So, of course, what you have to do is to take a regularization of this square root close to 0. Okay, but say essentially you see that somehow you kill the singularity just by dividing by square root of f. And you see that you can say, oh, but this is not the original equation. Yes, it's not the original equation, but I think it's not really worse than the Schrödinger equation taking psi here. Because somehow in the Schrödinger equation, the physical quantity should be psi square. Okay, if you would like to compute something, you need psi squared, not psi. So you should be able to write the equation for psi squared. So it's exactly the same. Okay, so that's a good point with the renormalization. You just use the entropy inequality, so the entropy, the relative entropy, and the entropy dissipation, and it's enough to say that everything here is well defined in the equation. So the first ingredient is renormalization. Okay, now you see, of course, it's not enough to say that everything is well defined to have a solution of the equation. It's the first step, but it's not enough. So you need a second ingredient, which is a little bit of compactness.
So can you say in more detail why you're not worried about this B? You said that the B is not important.
Okay, so maybe if you start with a B which is a constant, then you are happy. Okay, if you start with a B which is, so for instance in the case of art sphere, this is something which looks like V minus V1 dot omega, so it's like a power of V. Then you should be a bit careful to look at the weight everywhere to see that it's still well defined. So because here you see that you will get a square root of f1, and so you need to prove that square root of f1 times the power of typically times the modulus of v1 is also well defined. Okay, because say this guy will be integrable against b in L2 with the weight b, but now you have to prove that the square root of f1 here can support this additional power of v at infinity. Okay, so there is a bit of work here, but you can do it. Okay, so at this level, I don't want to make it more technical, but okay, there is and the same, you have to remove the singularity here. So there is still a lot of work to be done, to be honest. But this is just to give you the main ingredients. So one ingredient is renormalization, and typically the square root is a good renormalization. That's the idea. Now, of course, it's not enough to have all the terms which are well defined to have a solution. You need to somehow construct this solution. And so, if you imagine that you start with a very regularized version of this equation, then you should be able to take limits in this regularized version. And so, you need compactness. Okay. So the second ingredient is compactness. And here, essentially, it's complicated because, of course, you see that typically what you would like to be able to do is to say that in this, so maybe this guy will be only weakly compact, but then you would like to be able to multiply by this guy, and so you would like to have a little bit of strong compactness at some point. Okay, and so this is much more complicated because the kinetic equation is an hyperbolic equation. And so it's not true that you can expect to have strong compactness just because, say, hyperbolic equation, transport equation, all the singularities, they are transported. Okay, so the singularities will not disappear. They are transported. If you just look at free transport, but one thing with the transport is that you can have singularity, but somehow you have compactness on averages. Okay, so that's really the big breakthrough by Agoshkov and also by Lyon, Spertam, Goltz, Lyon, Spertam, and Tadmor. Goltz, Lyon, Spertam, and Santis. Sorry. So you have this averaging lemma. So if you have a control on dtf plus v grad xf, say which is equal to some s. And also you know that f, so if these two quantities, for instance, are bounded in L2, then it's not true that f will be more regular than L2, but if you integrate with respect to velocity, so you take any function phi, which is a smooth function, say with compact support, actually bounded is enough, bounded function with compact support in V. And you look at the integral of f v dv. So this function is still a function, so this is still a function of t and x. Okay, so this t x v, and you just integrate with respect to v. So you can imagine that it's just a truncation. Okay, you take just an indicator function of some set, but it can be any function that you would like to have. Okay, so if you look at this function will be in h1 half. Okay, so you have more regularity on this average than on the function itself. Okay, so you don't have any regularity on f, but you have regularity on this rho. So typically rho will be, say, so here I should say, okay, say I will take L infinity in time, L2 in x and v, and here I will take maybe T x and v. I think it's not really important. H1 half in x. This will be smaller than a constant times f in L2, L infinity L2, plus s in L2. Okay, so what is really important is that you have more regularity, and so you have compactness, strong compactness.
What do you mean here by compactness?
Compactness means that, okay, if you have a function which is, say, in L2, which is a sequence of function in L2, okay, which is just bounded in L2, okay, then you see that it will be weakly compact in the sense that it will have a limit in L2, okay, but maybe this limit is not strong enough in order that you can compute the limit of fn square. Okay, so maybe I should write this somewhere. So imagine that you have a function un, which a sequence of function which is just bounded in L2 with just one variable, okay, z. Okay, now this is enough to say that up to extraction this will converge weakly in L2. But this will not be enough to say that un square will converge to something. And so there are, say, the typical example for this are either oscillation. You see that if you take the sign of nz, this guy will converge in average to 0. But now if you take the square, it will converge in average to 1/2. So this is not true, at least, that the limit here is the square of this guy. Okay, and so the first problem is this kind of oscillations. The second problem is the problem of, so you have oscillations and you have also concentrations. So typically if I take here a function, so here it should be square root of n. Here it's 1 over n. Okay, so it's just the indicator function like this. So you see that in average, this un will just converge to 0. If I take the average against any function, I just not see anything. Okay, but now if I take the square, of course it's bounded, but it will just converge to the Dirac mass. Okay, so once again you have some trouble taking nonlinear limits if you have only weak convergence. Okay, so here it's exactly the same. I know that all this sequence of if I have an approximation scheme, I will have uniform bound in L2. So I know that I have some weak compactness. So I would like to say, oh, well, in the end, I will have a solution. But in order to do that, I should take limit in some nonlinear quantities here. And in order to take limit in nonlinear quantities, I need a bit of strong compactness to avoid this thing. Okay? So now you see that this averaging lemma, they tell you that you have strong compactness. So the fact that you have regularity here, it just prevents any small scale phenomena. Okay, so you will not have a very fast oscillation. You will not have concentration in T and X. And so now what you have to prove is that in this equation, actually, what is say somehow you have you can write everything in terms of average like this. Okay. And that's really important to just remove all these very small scale phenomena that could modify actually the limit. Okay. So I will not go further in this direction. Of course, here L2 is not enough. You should write some L1 version of this, but in L1 this is wrong. So you need a little bit of additional regularity with respect to V. So I think all these are a little bit too technical, but I think, so what is really important is to understand that the two important ingredients are really the renormalization and the compactness. And now I will just state the theorem by Di Perna and Lyons. And you see that actually this has really a physical interpretation, this problem, because somehow the problem in the Boltzmann equation, and it's also the problem when you like to derive this equation from the microscopic system, is that you can have some concentration at some point. It's not clear that all the particles will not be at the same point, and then you see that this low density limit will just disappear, and it's not clear what it means to have this binary collision process if all the particles are at the same point and everyone see everyone, so everything should be different. So this is not only a pure, mathematical complication just to be different from physicists. It's really the same.
I have a basic question.
Yes.
Okay, here I understand what you say, but you were you were saying in some sense you were close to Maxwellian or something.
Yes.
To justify that, but the theorem of deterministically is for any initial data or something like that.
Yeah. So actually, the original theorem by deterministically is close to vacuum in a certain sense, because you assume that you have finite mass and finite energy, and so of course if you are in the Wool space, this tells you that at infinity essentially everything is close to vacuum. So, but you can write essentially the same, being close to another equilibrium at infinity, provided that this equilibrium is the same, say, everywhere. So this is not the original version, but that's more or less the same. Okay, so I will just give one version of this theorem by deterministically, because I think I will not prove it. I just give you the two important arguments, and I think it's enough.
Is the father or
the son? Pierre-Louis. Okay, so here you assume that you have this grad cutoff assumption on B, and you assume that so that these are the assumption that say, so it can be in the Wool space. Of course, if you are in the torus, this is everything is equivalent because you had some constants everywhere, so it's not really important. But say in the Wool space, this assumption is enough to prove that then there exists a renormalized solution of the Boltzmann equation. So maybe I should precise that renormalized solution is not a solution that satisfy one the kinetic equation with one renormalization, but with any renormalization, which is admissible. So the only thing is that this renormalization has to be at least, say, at most like the square root at infinity, but it should be true for any function beta. Okay, so this means that you have dt of beta of f plus v grad x f beta of f equal beta prime of f q of ff, and this for any beta which is, say, smooth and smaller than and such that a beta of z is smaller than say square root of 1 plus z, something like this, constant. Okay, so the problem is that when f really concentrates, you need to do something. Okay, and so the good thing is that f satisfies the conservation of mass that I just erased, but so maybe I should say the local conservation of mass. So really dt of the integral of f dv plus divergence of the integral of fv dv equal to 0. Now it's a bit less good for the conservation of momentum. For the conservation of momentum, you have a kind of small correction, okay? So the local conservation of momentum with a defect measure. And the reason why, so you have something like dt of the integral of f v dv plus, so what you expect, so you would expect that this guy is equal to 0, but unfortunately, because you have only a control on the second moment of f, maybe you have something which remains at this point, and so you have a defect measure here. So this guy is a matrix which is positive definite, but still it's here, okay? And the entropy inequality with the same defect measure. So this means that you have a control on this. Okay, so you have this h of f m plus the integral from 0 to t of d of f plus the integral of the trace of m, which is smaller than h of f naught. Okay, so you control also this defect with the initial data. Okay, and of course, so that's, you see, it's not completely good because of this m. You have nothing on the local conservation of energy. This you lose completely. You don't have exactly the entropy inequality, and of course you have no uniqueness. At least it's not clear whether you can prove something. So uniqueness is open. Yes?
Maybe you said, but this M here?
It's a positive definite measure, matrix.
The statement is there exists M, and that's
yes.
You can. I mean, does it evolve in time? I mean.
Yeah, it depends on time and x. So m, so m of t and x, and the only thing that you know is positive. Matrix. You see, it's really you have a sequence of fn, vi, vj, and you only know that the integral of fn v square is bounded. Okay, so maybe you have some mass just flowing at infinity, and this you cannot do anything. So this will converge to essentially to f vi vj plus this m ij. That's just the.
But Laure, okay, let me ask you a very simple, much simpler equation, problem.
Yeah.
You are in a box.
Yes.
And you have data f which are not, your problem is really 0, so which are far away from 0, let's say uniformly. Then you can really solve the problem, uniqueness and so on.
The problem, when you say 0, no, the problem is not vacuum, the problem is really concentration. There are actually problems close to vacuum and close to concentration.
Okay.
So close to vacuum is just a problem of the singularity here to divide by square root of 0, which is...
Yes, so I say f is always far away from 0.
Then you still need to renormalize here.
You still need to renormalize.
Yeah, because the problem is that you cannot define f times f1.
Okay.
So here, this square root divided by square root is very good when f is large, because it will somehow kill the concentration. But of course, if you take exactly the square root close to 0, it's not very good.
So that's why I say f.
Yeah, so that's why you take a beta, which is something in between. So it's smooth, so it will not be like square root of f close to 0. You don't want to have the singularity, but really close to infinity, it's really like square root to kill the singularity. That's what you would like to do.
You're afraid of concentration at infinity in velocity space?
No, at infinity, concentration in the sense that f locally in x and v becomes infinite. So really concentration that all the particles would like to be at to sit at the same place in the phase space. That is really the problem. The phase space. Actually, the real problem is when they sit at the same x, because because essentially you cannot have really collision between two particles with exactly the same velocity. So if they are exactly at the same velocity and same x, it will not really be a problem. The problem is really when you have a lot of particles at the same x with all possible velocities, and then you see that somehow the important assumption that you have only binary collision, so they see each other just 2 by 2 and all these kind of things, this is completely wrong. If you have a lot of particles exactly at the same place, then you have a lot of problems, maybe even packing problems.
And there are no better evolution problems if I take very smooth initial data.
So I will. That's exactly what I will do now. Thank you very much. So of course, maybe I should say that this kind of solution, we absolutely don't know how to get them from the microscopic level. That's just dream, this level. So now there are a second way of looking at solution of this problem, so which are solutions close to equilibrium. And then for those of you who are familiar with fluid mechanics, this would be really the counterpart of Fujita-Kato. Okay, so this would be the counterpart of Fujita-Kato solutions for the Navier-Stokes equation. So what's the idea here? The idea is to say, okay, now this kind of concentration, they should not happen if I know that I'm really, really close to equilibrium, so F is not M, but M plus something which is not too big. Okay, so if this is the case, the first thing that you would like to do is to linearize the equation. Okay, so that's the first ingredient. So you look at the linearization of the problem. Okay, so you get, so imagine that you have that F is M times 1 plus G, and G should be small in the end. What you get is that dTg plus V grad xg will be a first term, which is the linearization of G, and I will write a minus here, plus a term which is a quadratic term, which is a Q of mg, and this is 1 over m. And here this L is just minus 1 over m, Q of mg. You see that the first term here, Q of m is just 0, just because m is an equilibrium. Okay, so the m is always this absolute Maxwellian.
By the way, the M you used here was not normalized. It has not the temperature of the system.
Yeah, but because at some point I just decided that temperature of the system is 1. But I could change everything.
No, but do you need M is really a reference M, which has nothing to do with the Maxwell distribution of the...
If you start from a system which at infinity is like this M here, what you see in x, if at infinity in x you prescribe the temperature to be 1, then what you expect is that, say, you have some fluctuations, but after a while you will see just everything with this temperature 1, because this is like a reservoir.
Okay, but here, I thought we were in a box.
If you are in a box, then you need to take the same temperature.
Ah, okay.
Yes.
Okay, there are two cases.
So here, yeah, if you are in the box, you need to take 1 here, if you would like to compare with this M. Yes. Thank you. Okay, so this is just this is nothing, just like a rewriting of this system here. But now you see that there is a very important property, which is, of course, related to the fact that you have this entropy dissipation, is that this operator here is a nice, very nice operator because it's just coercive. Okay, so that's the important point, is that this L, so of course it would be coercive in a space that I should write here.
What word did you use? Coercive?
I will tell you. Okay. Just be patient. So what you can prove is that lm of g, if you multiply by g, and you integrate with respect to m dv. So now just assume that g is a function of v. This will be greater than just the L2 norm of pi of g nu dv. So I will explain everything here. So I will write a mu because else it's a bit. Okay, so here the pi is just a projection. So now it's an orthogonal projection in L2 on the space which is orthogonal to all the conserved quantities. Okay, so pi is the projection of G on the space which is orthogonal to 1v and v squared. Okay, because of course you don't expect that this linearized operator can control this conserved quantities just because it's 0. Okay, if you take, this is the kernel of L. Okay, this part is just the kernel of L. Okay, so now if you project on the orthogonal of the kernel, then this is really a coercivity estimate. And you see that you have just a weight here, and this mu is just the integral of the cross-section with respect to omega. Okay, so this is just the integral of the cross-section with respect to v1 and omega. So it's just a function of v. And typically for art sphere, it's just something like v.
The fact that you say it is the kernel means that here you explicitly assume there are no other conserved quantities.
You can prove. I assume I prove. No, here I don't prove anything, but this is something that you can prove.
No, but if there were other conserved quantities.
Sure, it would be different.
Yes, so here you assume it explicitly.
Yeah. But this, you see that it's an assumption at the level of the Boltzmann equation. Once I have already written this equation, so it's not clear. Maybe you can have other conserved quantities that you lose in the. I don't know.
It's a question about B.
Yeah.
If B admitted some quartic invariant.
Yeah. So yeah. Yeah. The kernel will be larger. Yeah. Okay. So anyway, you see that this tells you that okay, there is this weight, but you see that it's even better actually that L2. Okay, so this tells you that you really control the parts of G which is orthogonal to the kernel. Okay, and so now with this estimate, you see that the argument, of course, I will not write everything now, but what I would like just to show you is with a simple ODE. Okay, why it's very good to have this. Okay, so imagine that instead of I now look at a very simple equation. So imagine that you have d of dt u is equal to minus lambda u plus u squared. Okay, so it's very simple ODE. Okay, and you see that that's very good because, of course, if you have just d over dt u equal u squared, it's very bad because you can construct a solution for a very small time. But you know that after this small time, it will blow up. Okay, you can even compute everything in terms of the initial data, blah, blah, blah. Okay, now if you have this minus lambda u, you see that it's very different because if you start from a u which is smaller than lambda, then you have a bound which is global in time. Okay, so the idea here is that with small data, so small data means that somehow u is smaller than lambda. Then you see that this right-hand side will be always negative. Okay, so this means that somehow if you have this coercivity here, if you start from something which is not too far from a fluctuation, which is really small somehow, then you will be able to control the thing for all times. Okay, and so that's really so these two arguments here, the coercivity and this kind of fixed points for small data are really the two arguments behind the theorem by Ukai. So I will just state the theorem by Ukai. Actually, there are a lot of variation around this theorem. So especially in the school by Go, and also Michler, Mouot. So I will not, but I just give you one statement to.
Anyway, why you erase the symbol greater or approximately equal to means there exists a
constant. Yeah, yeah, that is true. Yeah, yeah. This is just can write.
A physicist. No, just to understand.
Yeah, sure. Thank you. Okay, so theorem by Ukai. Is the one here. So you see that you will see that the functional space are a bit more complicated. So I will call HLK, which is the space of function G, such that this soup of 1 plus V to the K, and then you take M1/2 G, and in HL in X. So this guy is finite. Okay, so this is a Sobolev space. So typically it's like in X, you see that it's okay. You should take L sufficiently. So if you know this Fujita Kato, you will recognize everything. Okay. So now you take G0, which is in this HLK, for L bigger than 3 and K bigger than 5/2, and you assume that it's known. It's sufficiently small. Okay, and of course this A0 has something to do with the lambda, the lambda which is here. Okay. Then you have a unique global solution. Okay. Then there exists a unique global solution to the Boltzmann equation. And the solution G is in infinity in time, in H, LK, and also continuous. Okay, and that's it. Okay, so that's really. So you see that maybe I just can comment a little bit on this L. So L, when L is bigger than 3/2, so that's in dimension. I should say that it's in dimension 3. Okay, when L is bigger than 3/2, you see that this HL will somehow imply that G is bounded in infinity. Okay, so it's better because this is an algebra and blah blah blah, and you can deal with this. But essentially, this means that in X this is bounded. Okay, and then you end up with really the same kind of equation here. So to go from the transport to this, you just need to filter by the transport, but it's almost the same. Then you use the coercivity here. You just need to be a bit careful with the part which is in the kernel, but it's not really a big deal.
Yeah, our question was the kernel here is included. So, okay, if you don't have the problem of the orthogonal of the kernel. So
you see that actually in the kernel, you can control, say, the p-perp. So maybe it should be p-perp to be NP, the projection on the kernel. But you see that if the projection on the kernel, you know very well what it is. So once you control this norm, actually you control the kernel, just because it's a combination of 1v and v squared. So as a function of v, it's a very, very nice function.
okay,
It's much better than L2. Or
here you use that L is big enough. So
yeah, what is really important is L big enough. So it's really, say, this is really for the dependency with respect to x that you use. And for the dependence with respect to V, it's not really. Yeah. Okay, so you see that this seems to be very interesting because here you have no concentration. Okay, so you can say, okay, so let's do the same for the microscopic system, and then we will be very happy with this setting. The problem is that here you see that the fundamental, in both approaches, the fundamental thing is the fact that you have some coercivity, okay, or that you have some dissipation. Okay, so that's really the important point. The point you see that this coercivity is really the way you express the dissipation, because the L2 norm is just a linearization of the entropy, of the relative entropy, and so this coercivity is a kind of linearized version of the entropy dissipation. Okay, so you see that in both approaches, the crucial argument is the dissipation. Okay, but now we will see tomorrow when we will look at this Boltzmann equation as a limit of microscopic system. In the microscopic, you have no dissipation. Nothing is dissipated. Everything is Hamiltonian. Everything is conserved. Okay, so this means that you cannot really use that. You can use that to have solutions of the limiting equation, but you have no counterpart of this at the microscopic level. Okay, so this means that somehow we will need to use something, an even different approach. Okay, so maybe that's the last thing that I would like to say today is which functional setting we will use for the limit. And this and here you will see why this Lanford argument somehow stops for a very small time. Okay, so now I go back to this equation, dtf plus v grad xf equal q of ff. But now what I say that I'm not able to use the entropy dissipation. I'm not able to use really this. You see that and somehow the entropy dissipation is based on the fact that you have this minus sign and that you have these symmetries and that then you have some cancellation and so on. And now I'm not able to use this. Okay, so the only thing that I can do is to say, oh, this guy is the integral of f prime 1 minus ff1, and then I integrate with respect to b dv1 d omega, but I'm not able to see this minus sign. Okay, so if I cannot see the minus sign, let's do like as it was just a plus, and then what you do is just to say, okay, maybe I can do I can construct a solution of this equation by a fixed point. Okay, just forgetting about the minus sign here. And so if you use the counterpart of this, what you have is just dt t over dtu equal to u squared. Okay, so you have a first problem, which is a problem that here is quadratic. It's a quadratic function. And if you cannot see the minus sign, then it cannot be better like this. Okay, so yeah, it will be because you can construct a local solution of this. Yeah. So that's the first problem. So the first problem is the fact that you have a right-hand side which is quadratic. Okay. And then there is another problem that I will not discuss a lot in the sequel because it's more technical, but still it's an important problem. That if you remember, what I said is that in the case of art spheres, what you will find is that the b of v minus v1 omega is the absolute value of this scalar product here. So typically it grows like v plus v1. Okay, so somehow the way you can control this is like this. Okay, so this means that even though you would like to construct a solution without thinking too much, so you say, okay, I will take the L infinity norm, Okay, so the transport is very good because at least the L infinity norm is preserved. And you say, okay, about this, let me just replace everything by the L infinity norm here. Okay, so it will not be good, it will be like this. But still it's not enough because L infinity norm will not absorb this power of V and V1 and the integral here. Okay, so this means that you will lose something each time. Okay, so you have, so the second problem here is that you have a loss continuity estimate in V. So typically what you will use are spaces like, so you take the soup of exponential of beta V square times f of t xv. So that's what you would like to, in x and v. So that's for the kind of norm that you would like to use. Okay. But you see that each time you will take this norm here, you will have a loss on the Q of ff. Okay, so this means that you have a loss both due to this right hand side, which is quadratic, and also because you have this loss in velocity here. Okay, so essentially what you have to do is to do a fixed point in a space where this beta here will depend on time. Okay, so that's not very nice, but that's the way you should do it. Okay, so now the space, okay, the functional space actually depends on time. Okay, because you will take beta to be something like beta naught minus lambda t. Okay, so this means that you will, of course, in the end you will have a short time results. The first reason why is that the beta should remain non-negative, and so you see that t cannot be more than beta naught divided by lambda. And okay, you have no choice, and the decay at infinity. Okay, so essentially you assume that you start from Gaussian, but this Gaussian, say when time grows, they are more and more flat. Okay, and okay, so then you have essentially there are two reasons why you are not able to go further by this very simple, well, it's not really simple, but should be the simple way of constructing solution. But you have two obstructions. The first one is this nonlinearity here, and the second one is the loss with respect to velocity. Okay, so this problem will be, of course, technical, the problem of the control of large energy, but somehow it will pop up everywhere. Okay, so sometimes I will just forget about it, but essentially it pops up everywhere. Okay, I think it's time. I thank you very much for your attention, and of course I'm available for questions.
More questions?
Recently there has been work on the future information and how it can be used to produce global large data solution. So how does it fit this picture? How does it act on this issue of somehow global, like either quadratic or velocity? I don't know.
So the first thing is that as long as you are just interested in the Boltzmann equation, you can use this entropy dissipation or dissipation. So, and it's really important. So you are not really. So what I said is that just coming from the microscopic scale, you are not really able to see the cancellation between the two terms. So you don't see the dissipation and blah blah blah. Okay, so you have no choice. At some point you need to look at this kind of solutions. If it's not the case, then you can go back to this or to renormalized solution, and you see that somehow if you already know that if you are able to prove that the f is in L infinity, then the renormalization is completely useless because it just can be identity. Okay, so if you are able to improve the a priori bounds that you have, and actually the point is that you need both bound from below and upper bounds. But if you can improve the kind of bounds that you have, then you can make this theorem to be somehow, yeah, a real nice smooth solution. So really the problem is to control this vacuum and concentration mainly.
And does the Fisher information do that?
Say, to my knowledge, but there will be a seminar next week on this. It's 2 seminars. It's still a conditional result. You still need to.
They don't bootstrap the.
Yeah, they bootstrap, but I think they have not a result like take an initial data like this without any restriction on the size and without anything, and then I can produce a solution. But I'm not sure. But yeah, the idea is really to improve, and I think it's for the Boltzmann equation without cutoff.
And spatially homogeneous.
Yeah. So that's spatially homogeneous, of course, is a big thing, and the thing is that of course maybe this is a comment that I can do. So when you have no cutoff, somehow it's more complicated because you have a singularity in the B. Okay. So in particular, if you would like to come from the microscopic scale, you see that you have this. You say, oh, I cannot use the minus sign, but this guy is not integrable, then this is the end, okay? Because you have not u squared, but u squared times plus infinity. So, end of the game, okay? Now, if you are already at the level of the Boltzmann equation, so you have a singularity here, but the singularity here tells you that if this guy is still finite, then this means that you have cancellation between these 2 terms. Okay, and so the point is that close to grazing collisions, essentially this entropy dissipation gives you some regularity. So that's something that now is, so you have many functional inequalities which tell you that with this d of f, you can control a little bit of regularity with respect to v, but then with the transport you can transfer some of this regularity with respect to v on regularity with respect to x. Okay, so that's the idea behind this solution without cutoff. But okay, to my knowledge, in the inhomogeneous case, this is still a conditional result. You still need to. It's not enough to control everything.
Some more questions? Yes.
I have a very nice question about controlling the x dependent f. Like a naive approach I would use would be like to integrate over 1 over x minus y, for example, ftx, fty. And
yes.
If you have some algebraic properties that make you can control it. Do you know if some people tried it or? So
actually, in dimension 1, this is something that I didn't discuss, but there are solutions constructed by Bonny, I think. So there are weak solutions because he uses something like this, which is the counterpart of, for this hyperbolic system. I don't remember who. The doubling of variables. Okay, so I think it's Legenskaya or no? Right. Okay. Yeah, the school of Khrushchev and Oleinik, maybe. Russian. So yeah, in dimension 1, you can use this kind of doubling of variables, and then you can define. You can really define without renormalization. But in higher dimension, I don't think something like this is known. Only in dimension 1. But actually, in understanding everything in dimension 1 would be already great. But
okay, so maybe okay, tomorrow same time. See you.